welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler, and today we'll be doing Unit 5, Lesson number 8, on the midpoint formula. Unit 5 is devoted to learning the tools of coordinate geometry. And one of the tools is going to be how do we find the coordinates of the midpoint of a line segment if we know the coordinates of the endpoints. So before we kind of jump into what that formula is, or better yet, discover that formula, what I'd like to do is do some basic review about midpoints. Now this is probably something that you already feel quite comfortable with, but let's talk about it a bit. Exercise number 1. In the diagram below, segment CD bisects segment AB at point M. Based on the information given, letter A, M is the midpoint of which of the two segments? Explain. Alright, this should be very, very easy for you. We've worked with midpoints extensively. M is the midpoint of which of those segments? Hopefully, you said segment AB. Okay, and that's because CD cuts AB in half, right? CD is the bisector of AB, right? Great, easy enough. Letter B. Which two segments must have the same length based on the givens? Make a formal statement of congruence. So do that. Which two segments in this diagram, based on the fact that M is the midpoint of AB, have to have the same length? Alright, well that would be AM, right, must be congruent to BM, right? These two have to have the same length because that is the definition of a midpoint. A midpoint is that one unique point on a line segment that divides it exactly into two congruent segments, two segments of equal length. Those two happen to be AM and BM. Alright, so simple enough. Let's now look and move to the coordinate plane. Alright, here we go. Midpoints and coordinate geometry. Midpoints and coordinate geometry. Exercise 2. In the diagram shown, MN contains point P. Use the distance formula to prove that P is the midpoint of MN. So I want to prove that P is the midpoint of segment MN by using the distance formula. Now, we learned about the distance formula actually in the last lesson. Hopefully you've already learned it. If you haven't, then this one is going to be a little bit of a struggle for you, just this first exercise. You could probably get away in later exercises without knowing the distance formula, but let me write that down for you. Right? The distance formula is the square root of x2 minus x1 squared plus y2, come on, minus y1 squared. Right? So if you think about it, the way that we can prove that P is the midpoint of MN is by showing that the length of MP, right, is equal to the length of PN. Why don't we do MP together, and then you can do PN on your own, all right? So let's do MP, all right? Its length, or the distance between M and P, will be given by 10 minus 2, that's the change in x, squared, plus 9 minus 3, that's the change in y, squared. Alright, 10 minus 2 is 8, squared. 9 minus 3 is 6, squared. We'll get the square root of 64 plus 36. That gives me the square root of 100, which is 10. Alright, so MP has a length of 10 units. Now, go ahead and figure out, calculate the length of PN using that distance formula. Take a few minutes for that. Alright, let's go through it. Alright, so PN. Okay, I'm going to use these 2 points now. The distance will be 18 minus 10 squared plus 15 minus 9 squared. All right, 18 minus 10, again, is 8. So we get 8 squared. 15 minus 9 is 6. Again, square it. Just like before, when we add those two together, we'll get the square root of 100, which is also 10. Right, and that really truly does prove that P is the midpoint of MN because it divides it into two segments that have the same length. One of the things that students tend to like about coordinate geometry is that there are numbers that you can really grasp onto and see, right? This is in a huge contrast to the Euclidean proof that we've done a lot of so far, where it's more just, being told, hey, this side is congruent to that side, which means that they would have the same length, but maybe you never know what those lengths are. Here, very solid. The length of segment MP is 10 units, the length of segment PN is 10 units, and therefore P must lie at the midpoint of that line segment. Now, let's try to figure out, though, without the distance formula, how we can come up with that midpoint. This goes into exercise number 3. Exercise 3 says, given M, 2, 3, and N, 18, 15, from exercise number 2, find the average of their x-coordinates and the average of their y-coordinates. What do you notice about these averages? Well, I certainly hope you know how to find the average of two numbers. So go ahead and then see if there's something that's kind of obvious about those two numbers you come up with. All right, well, to find any average, you add up all the numbers involved and divide by how many there are. When there's just two numbers, we just add those two numbers up and divide by 2. So for instance, the average x-coordinate would be 2 plus 18 divided by 2. And that's going to be 20 divided by 2, and that's 10. All right, whatever. The y-coordinate average would be 3 plus 15 divided by 2, and that's 18 divided by 2, and that's 9. So really, you could think of that as being the point 10, 9. And do you notice anything about the point 10, 9? Well, let's do it in red so that it's a lot more obvious. 10, 9 is, in fact, the midpoint. So how do you find the midpoint of any line segment? You average the x-coordinates and you average the y-coordinates. And that should make sense. Generally speaking, averages are a little bit hard to get a feeling for. They're very easy to calculate, add up all the numbers, divide by how many there are. But when you have two numbers, just two numbers, and you average them, like I've got average 5 and 7. 5 plus 7 is 12 divided by 2, and I get 6. The average is the number that sits right in the middle of the two, and therefore it makes a lot of sense in terms of the midpoint. So let's kind of summarize this in the next slide with the midpoint formula. All right. Now, the midpoint formula really rounds out the three extremely important formulas of coordinate geometry. The first being the slope formula, the second being the distance formula, and now the midpoint formula. The midpoint formula, no great surprise, comes in the form of a coordinate point. But here's the key, right? If you've got a line segment that's got endpoints at x1, y1, and x2, y2, then to find the midpoint, all you have to do is average the x and average the y. That's it. It is the easiest, in my personal opinion, of the three formulas to use. Ironically, it seems to be the one that students struggle the most with. And yet, average x, average y, and you've got the midpoint. So let's get a little practice with that. No square roots involved. Nothing really particularly messy. All right. Exercise number 4 says, for each set of coordinates, find the coordinates of the midpoint of the segment joining the two. All right. So let's say I've got a segment that's got these two endpoints, and I want to find the midpoint. So what do? Well, I take negative 5 plus 9, the two x-coordinates, and I divide by 2. Negative 5 plus 9 is positive 4. Positive 4 divided by 2 is 2. That's my average x-coordinate. My average y-coordinate, on the other hand, would be 7 plus 15 divided by 2, which is 22 divided by 2, and that's 11. So the midpoint of a line segment that has these two coordinates as its endpoints is 2, 11. You don't get much easier than that. Why don't you go ahead and do it for those two coordinate points? All right, let's go through it. You can kind of lay it out as x average, y average, or you could do it all within sort of the parentheses like this. So I could do something like this. I could say, well, I have negative 8 plus 5 divided by 2, comma 12 plus 4 divided by 2, right? That will give me negative 3 divided by 2 and 16 divided by 2. Now, of course, negative 3 is not nicely divisible by 2, so what should you do? Well, you could leave it as negative 3 halves. That would be fine. You could write it as negative 1.5, or you could even do negative 1.5. All right. If your teacher has a preferred way for you to leave an answer like that, I would follow what your teacher says. I personally don't have any problems with decimals. I kind of like them. So I think I would probably say negative 1.5 and 8. Negative 1.5 and 8. The midpoint formula. What more is there to say? The distance formula is kind of challenging. Subtract, subtract, square, square, add, take the square root, possibly simplify radicals, all that kind of business. The midpoint formula, find the average of the x-coordinates, find the average of the y-coordinates, and you have the midpoint. It's pretty nice. Okay, let's get a little more work with this. Not much though, because there's not much to say, right? Let me change back to blue real quick. Let's take a look at about the most challenging problem we're going to do today, exercise number 5. In the graph below, AB is drawn with endpoints at negative 1, negative 3, and 3, 7. Letter A asks us to find the coordinates of the midpoint of M and mark it on the graph. Great. All right. So why don't you go ahead and do that procedure. Just use the formula. Trust me, use the formula and come up with the midpoint based on those two coordinate points and then plot it. And then we'll revisit the problem. All right, let's go through it. Again, pretty easy. Take the x-coordinates, negative 1 plus 3 divided by 2 equals positive 2 divided by 2 equals 1. That's my x-coordinate. My y-coordinates will be negative 3 plus 7 divided by 2 will give me 4 divided by 2 will give me 2. So the midpoint looks like it's got coordinates at 1, 2, and that's right there. All right. One of the nice things is that visually speaking, it looks right. And also, of course, if we got a point that didn't even lie on that line segment, we would definitely know that it was wrong. So if I had done something weird like, I don't know, average these two and then average those two somehow, I don't know. You know, we would get a point that wouldn't even likely lie on the line segment. So that, at least, we know lies on the line segment, and it definitely looks like it's at the midpoint. All right, let's take a look at letter B. Letter B says, what is the slope of AB? State in simplest form. So I just want to know the slope of AB. Why don't you go ahead and do that? All right, let's do it. Now I'm going to be kind of formula driven here. We could do it graphically, but I'm going to try to review every one of the major coordinate geometry formulas in this lesson. So the slope formula, y2 minus y1 divided by x2 minus x1. That'll be 7 minus negative 3, all divided by 3 minus negative 1. Gives me 10 in the numerator, 4 in the denominator. I can reduce both of those by dividing both by 2, and I get a slope of 5 halves. All right, so the slope of AB is 5 halves. Now, letter C. Draw the perpendicular bisector of AB. Draw the perpendicular bisector of AB and state its equation. So now, I want to draw the line that bisects AB, so it's got to pass through the midpoint, and is perpendicular to it. Do you remember what the relationship is between the slope of AB and the slope of a line that's perpendicular to AB? Well, the perpendicular line will have a slope that is the negative reciprocal of AB. So it'll have a slope of -2/5. See if you can use that slope now to draw the perpendicular bisector, and if you can remember how to write its equation, and I would suggest writing its equation in point-slope form instead of slope-intercept form, go ahead and do so. But first, draw in the perpendicular bisector. All right, let's go through it. Well, we know we've got a rise divided by run of -2/5, which means I'm going to go 5 units to the right and 2 units down to get my next point, or I can go 5 units to the left and 2 units up. I think I'll do one more of those. All right, so all those points line the perpendicular bisector. Is that right? Let me just make sure. Yep, okay, great. And I don't have a ruler. Let me go grab a ruler real quick. Thank you. Go back to full screen. And now let me use my ruler. And draw that perpendicular bisector. Remember, not to minimize it, but one thing that is true is that the perpendicular bisector must go through the midpoint. It must. Now, let's write its equation, okay? Does it have a nice y-intercept? It doesn't particularly, right? The y-intercept of the perpendicular bisector isn't particularly nice, so using y equals mx plus b, not a great choice. On the other hand, a few lessons ago, we learned about what was called the point-slope form of a line. Y minus y1 equals m times x minus x1. Okay, and the beautiful thing is, we know a very nice point that lies on that perpendicular bisector, specifically the midpoint. We also know its slope, -2/5, so we can write the equation by just doing this. Y minus 2 equals -2/5 times x minus 1. Right? And again, all I'm doing is using the point 1, 2 in this general form, y minus y1 equals m times x minus x1. I'm using the point 1, 2. And then I'm getting the slope, -2/5, from that perpendicular relationship. All right. One last little piece. Letter D. Letter D says, state one point other than M that the perpendicular bisector passes through. Mark this point as D on the graph, draw AD and BD, and find their lengths using the distance formula. What do you observe? Well, there are obviously an infinite number of points that lie along that perpendicular bisector, but there are some that are nicer than others, right? For instance, there are the 3 points we marked, here, here, and here, that are particularly nice. This part of the exercise works with any of those 3 nice points, or even any of the not so nice points. I'm guessing we want to stick with one, though, that's pretty nice. So, let me pick one. Okay, let me go with one that makes sense. I'm gonna go with red here. All right, and I think I'll just use this. Specifically, I'll use the point -4, 4. That lies on the perpendicular bisector. So let me just kind of throw that down in here. -4, 4. And then what the problem also asked me to do was draw in AD. Let me label this as point D. To draw in AD, come here, Ruben, come back to me. There we go. Draw in AD and BD. I think I'll just stick with it in red to contrast that nice blue that we've got up there. So here's AD. And here's BD. And now we'll get rid of our ruler. All right, and what I'd like to do now is I'd like to actually calculate the length of AD and the length of BD. Okay, real quick, I think what I'd like to do is write down the coordinates of A and B before we... A is negative 1, 3. B is 3, 7. And now let's figure out the length of AD and the length of BD and make an observation about it. Okay? Let's do AD together and then you can do BD. So here's D, and here's A. Let's do the distance formula. All right? It's square root of negative 1 minus negative 4 squared plus negative 3 minus 4 squared. All right? Again, all I'm doing is using the distance formula with point A and point D. Negative 1 minus negative 4 squared, negative 3 minus 4 squared. That's it. Let me keep going. Let me extend my page a little bit so I have an easier time writing. Negative 1 minus negative 4. Be careful, right? That's going to be a positive 3 squared. Negative 3 minus 4 is negative 7 squared. All right, 3 squared is 9. Negative 7 squared is 49. And I get the distance is the square root of 58. Now, 58 is not a nice perfect square. All right, so what should I do with this? Well, I see no reason to do anything with it other than leave it as the square root of 58. Just leave it that way. I mean, I could also write it to the nearest tenth or something like that, but why not leave the answer exact as the square root of 58? Now what I'd like you to do is work out the length of BD by using point B and point D. Let me move this out of the way. All right, take a few minutes to do that. All right, let's go through it. Again, just using the distance formula. The distance is the square root of 3 minus negative 4 squared plus 7 minus 4 squared. All right, 3 minus negative 4, be careful, is 7. 7 minus 4, that's easy as 3. 7 squared is 49, 3 squared is 9, and I get the square root of 58. So what observation can we make? Well, oops, this length is the square root of 58. This length is also the square root of 58. So the observation I can make is that point D is equidistant from A and B. And I'm hoping that sounds familiar to you, right? Time and time again, we've talked about the fact that any point that lies on the perpendicular bisector of a line segment should be equidistant from the two endpoints of that line segment. Now I pulled off point D here, but I could have pulled off this point, or I could have taken this one down here. In each case, we wouldn't have found the square root of 58, but we would have found that both of those line segments, AD and BD, were the same length, hence proving something, or at least showing or illustrating something that we already knew to be true. Any point along that perpendicular bisector will be equidistant from points A and B. All right, let me step back a little bit, allow you some time to copy down anything here you need to. Let me pull the page down a little bit. Anything here? Okay, and let's wrap up. So, today what we saw was the last of the three major formulas that we need in coordinate geometry. Those three formulas are the slope formula, the distance formula, and the midpoint formula. To me, the midpoint formula is the easiest of them all and the most understandable. We simply average the x-coordinates, we average the y-coordinates, and we're in the middle of the line segment, because that's what averages of two numbers do. All right, we'll now be able to use these three formulas moving forwards to do all sorts of different things with coordinate geometry and prove different properties of various figures. Okay, for now I'd like to just thank you for joining me for another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.